This video is about the Big Bang Theory, what it is, and more importantly in my mind even, what it isn't, because there's so much confusion about what the Big Bang Theory is and everyone seems to think it's an explosion that started the universe, and not exactly, that's not exactly what it is. So, the important thing to remember is that the Big Bang Theory is this, it is a theory. Now a theory is this, a concept backed up by evidence that is not yet verified, but that if true, would explain certain observations. So the Big Bang Theory, we're not completely sure that it's true, but if it is, it describes what we see. It is backed up by evidence, so it's not been plucked out of thin air and someone's just made it up. They do have evidence for it, but we haven't got enough evidence yet to say this is exactly what happened. And there's a lot of theories in science. There's a lot more than you think that we're not completely sure is true. But the Big Bang Theory is probably the most popular or most well-known one. So, here's what the Big Bang Theory is, okay? It is that in the distant past, the universe was very dense and hot. Since then, it's expanded, becoming less dense and cooler. And that's it, really. It just means that years ago, so here we are now, this is the present, so you can see lots of galaxies all nicely spread out. In the past, they were closer together again, and closer together again. So this is in the past, where the galaxies were closer together, or everything, not just galaxies I should say, all the matter in the universe is closer together, that makes it more dense, and because of that it was hotter as well. So this, if they ever ask you what is the Big Bang Theory, this is it. So what is it not? It's not a theory about how the universe began, because it doesn't tell us exactly how the universe began in any way. We don't know what happened before this point, okay? We're pretty sure about what happened since the universe began from about, say, 0.0000001 seconds. But we don't know what happened at the very start, and we don't know what sparked that off, okay? So we don't know how it exactly began. It's how it evolved since. It's really important, is it's how it's evolved is what it talks about. So the Big Bang Theory is about how the universe evolved, not how it began. It's also not necessarily a big explosion. Now, it could be, but we're not sure because we don't know about that first, not even pico nanosecond. We don't know about the first instant, so it might have been an explosion, but it wasn't necessarily an explosion. It also doesn't say there is or there isn't God in any way. So it doesn't verify nor refute the fact there might be a God, because it's not mentioned in there, but in nowhere in the Big Bang Theory does it say this this happened because there was no God. Nowhere does it say that a God sparked it off. It doesn't mention God in any way. So that's a really quick introduction to what the theory is. In the distant past, the universe was very dense and very hot. Since then, it's expanded, becoming less dense and cooler. Now, there are four main pieces of evidence for the Big Bang Theory. As we've said here, it's really important, and we're going to go through these piece by piece. Okay, there's four pieces of evidence that we're going to talk about that's important for you to know about. Now, the first one is the age of stars. Now, the Big Bang, we think, happened about 14,000 million years ago. Now, as I said in a previous video, 14,000 million is, in American terms, a billion. But in England, we say 1,000 million, because a billion in England is a million. So the Big Bang happened, if it's right, about 14,000 million years ago. Now, the oldest stars that we know of are about, oldest stars are about 12,000 million years old. Now, this supports the Big Bang Theory, because it shows we haven't found anything that's older than the supposed start of the universe, okay? If I found a star that was 16,000 million years old, then obviously the Big Bang Theory would be wrong, because something would have happened before then. So the fact that we haven't found one that's that old is evidence for it. Now, there's better evidence out there as well, which we're going to talk about now. Now, you may know that light is actually a wave, okay? So light is a wave. Now the colour of light depends on how big the wave is. So I can't really draw this completely because I haven't got time. But if I draw it like this, you'll see we have red, then orange, it's in the spectrum, then yellow, then green, then blue, and then purple, or indigo and violet. And you should be able to see that as I've gone along, I've tried to make it so that my wavelength, which is this thing here, my wavelength is longer for red. Okay, so longer light is red, shorter light is blue or purple. Now, when you look at a galaxy, the light that was emitted from Earth travels towards Earth like this. And here I'm going to draw 1, 2, 3 wavelengths. Okay, that's 3 complete waves of normal yellow light. Okay, most stars emit a yellowish light that we know about. Okay, so there's 3 stars of yellowish light. Now, if that galaxy is moving towards Earth, the light changes a bit because I still need to have 3 full waves of light between me and the galaxy. So if the light is moving towards Earth, that light gets squashed up. So let's see if we can draw this. 1, 2, 3. That light becomes squashed up. Now I've drawn this in blue because if we squash light so the wavelength is smaller, it goes towards the blue end of the spectrum. So it gets, this way is squashing. Hope you can see that up there, yeah. This way is squashing. So it becomes what we call blue shifted. And it's kind of like having a slinky. If you have a slinky, you imagine this light to be a slinky. If your galaxy is one end of the slinky and your Earth is the other end, or there's 2 people holding it, if they get closer together, the coils of the slinky get closer together, the wavelength gets smaller and it becomes blue. Now I'm sure you can imagine now, if instead that galaxy moves away from us, what happens is that the light stretches. So I need 3 complete waves again. 1, 2, 3. And this time I've drawn it red because if I have 3 complete waves, I've stretched it, and so it's gone more towards the red end. So this is stretching. So the light has been stretched, and this is called redshifted. So a galaxy whose light's been redshifted must be moving further away from us because the light has been stretched away from us. Okay, and we find that most galaxies are like this. Most galaxies are moving away from us. Now, there's a couple that are blue shifted, like Andromeda, which is the closest galaxy to us, 2.5 million light years, is actually blue shifted a little bit, not very much because it's so close, but it is moving towards us because in a couple of billion years, then we will collide together, not even a couple thousands of them. We will collide together because it is moving. But generally, most galaxies are moving away from us. Now the thing is, they're all moving away from each other as well. If you imagine blowing up, having a balloon, drawing a balloon like this, here we go, and putting little stars on it. Now, if you measure the distance between those stars, and then calculate it, and then you blow that balloon up, so it's much, much bigger, like so, and you look at those stars again, you'll see that every single one of those distances that I drew an arrow for has got bigger. And that's what it's like in the universe, okay? The galaxies are all moving away from each other. Galaxies are all moving away from each other. Okay? And that's really important for the next step, which is the next piece of evidence. Okay? That's called Hubble Expansion. Now, Edwin Hubble was a really famous astronomer about 100 years ago, and he plotted the speed of the galaxy and the distance of the galaxy, and I'll explain that now. So, something that's moving away from you faster will be more redshifted. So the more redshifted something is, more redshift must be moving away from you quicker, okay, moving away faster. It's just a fact of how redshift worked. So a galaxy that's more redshift has got a higher speed. So Edwin Hubble calculated how far away it was to these galaxies, and he also calculated how much they were redshifted, and so worked out the speed of them. With complicated, confusing calculations you don't really need to know. But he plotted a graph of the speed of the galaxy and how far away they were from us, and he found that he got this kind of relation. Now, it wasn't the world's best graph, it wasn't perfect, but there was a clear correlation, a clear positive correlation like this. Okay, he found that the further away a galaxy is, the more redshifted it is, and so the faster it is moving away from us. And that means, overall, a really important thing. That means that the universe, oh, I've not spelled that right, there we go. Universe is expanding. And before this, people thought the universe was just still. It wasn't in any way moving. Okay? It also means that it's expanding at an increasing rate. But you don't need to know about that bit just as much right now. So, the universe is expanding, and we know this because of Hubble expansion. Now, if the universe is expanding, if it's all far apart now, and it's going to get further apart in the future, if you think about going back in the past, it must have been close together, and close together, and close together, and close together, and back into a tiny point. And if we look back at our very first piece of paper, at the Big Bang Theory, the Big Bang Theory is that in the distant past, the universe is very hot and very dense. Since then, it's expanded. So Hubble proved the universe is expanding, like the Big Bang Theory says. So that's one of the real big pieces of evidence for it. Now, the final bit of evidence is called the cosmic microwave background, and this is probably the hardest one to get your head around, because you can't really go into much detail about it just now, because you don't know enough of the science yet. It's really, really hard stuff. It's like A-level, degree-level stuff. But the important thing to know kind of is the dates. So in 1948, this first step happened, okay? A group of scientists predicted that an afterglow of the Big Bang should fill the whole universe with microwaves. That was in 1948. You should, if you point a telescope anywhere, see some microwaves, okay? Because some telescopes can see microwaves, or they can detect microwaves. Now, no one really found this until in the 1960s. It's quite a funny story. Well, physicists. Some engineers in New Jersey were using a new telescope, and they were pointing it in a place in the sky. They were getting this really funny noise. And what they actually thought, there were lots of pigeons around, so they thought it was pigeon poo, basically, that was causing this. So they cleaned it all off and tried again. With a clean telescope, they still got the same thing. They pointed it in different directions, still got this really weird, odd hissing noise. And they realised, eventually, these scientists were on the lookout, and they realised that these engineers here had accidentally found this cosmic microwave background. Okay, they found the afterglow of the universe. And that's a really big point, because if you have a theory that fits around things you've seen, it's not as good as when you make a prediction and then you find proof of that prediction. So using the Big Bang Theory, they predicted that they should see this afterglow, and then they found it. And this is actually what the cosmic microwave background looks like. Okay? It's the same in all directions. It's the same everywhere you look in the universe. And it's a really, really important piece of evidence for the Big Bang Theory. Now, the Big Bang Theory says that the universe is expanding. So the really next question is, will the universe expand forever? Well, actually, that depends on one really important thing. It depends on the mass of the universe. Everything in it combined together. Now, you can see here that I've got a size of the universe versus time graph. Now, I've drawn this graph wrong on my computer. It should be the other way around. This should say size of universe. Oops. And this should say time. Oh well. There we go. So, size of the universe versus time. Now, if the universe expands forever, it's just going to get bigger and bigger and bigger and bigger and bigger and bigger. And it'll be a nice graph like that, positive correlation. Now, this is going to happen if there's a low mass, okay? It'll expand forever. Now, what also could happen is it could expand and then come back and contract, okay? So it's expanding here, and then here it gets to a critical point, we say, and then it starts to contract. So this is expand and contract, and this happens for a high mass. This happens because there's so much gravity, there's so much mass, there's so much gravity in the universe that eventually it collapses back in on itself. So it's to do with gravity. So it expands and then contracts. And this is also known as the Big Crunch, which is what you might have heard of before, the Big Crunch. Okay, now we're about here in time on this axis here. So we're not actually sure if it's going to carry on like this or carry on like this. And it's really hard to work out how much matter is in the universe because of a really big thing that you might have heard of in the news called, or on TV, called dark matter. Okay, so we don't really know how much matter is in the universe because we can't see most of it and we haven't got a clue what it is. So it's really hard to measure the mass of the universe, and if we could, we'd know what was going to happen. But we can't right now. We're trying really hard. We're really not sure right now what one it's going to be. But we'll hopefully find out in the future. But we need to know that there's two possible fates. It can either expand forever if there's a low mass, or it can expand and then it can contract in the Big Crunch. So that's really everything we need to know about the Big Bang Theory. It's a lot simpler than most people think. And it's got 4 pieces of main evidence, and this comes out of it at the end as well. Hope it helps.